In the last video, I introduced to you finding surface area using integration, and we ended up getting a little weird answer. So what I want to do in this video is give you some more practice and help us confirm to ourselves that what we did in the last video and talking about surface area and how we find that using integration makes sense. And what we're going to do is find the surface area of a sphere with radius b. So using what we saw in the last video, why don't you pause the video and try to find the surface area of this sphere with a radius b. All right. Assuming that you've given it a go, I think a first step here, I've plotted out this circle, but what we're going to do is take a half of this circle here, and we're going to end up rotating it about an axis. So I'm going to choose this top half here, top half of this circle here, and then I'm going to take it and rotate this curve around the x-axis, and that's going to give us our sphere. And writing out what this curve is in blue here, that's just going to be solving this equation for the circle for y, and we're going to end up taking this positive root. So we're going to get this. We have y squared is equal to b squared minus x squared, and then we'll take the positive root of that. So this curve here in blue is y is equal to the square root of b squared minus x squared. And we took this curve and rotated it around the x-axis, and now we have this sphere that we're looking at with a radius b, and we want to find its surface area. And in order to do so, what I'm going to do is take these vertical slices. So I'm going to take these vertical slices like this. And we saw something similar in the last video. Take these vertical slices. And before I pull this out and we start to look at it, where are we headed? We want to ultimately get a definite integral with that's going to be summing up all of these little pieces of surface area. That's where we're headed. So in order to do that, let's pull this slice out and start to look at it a little bit. This is a circle here, and it's going to have a radius. It's going to have a radius, and we can plot that up here as well. So we'll have this guy going right there. That's not great. Here, a little more right there. There we go. And we have this circle here and its radius. And in order to get this little piece of surface area, we saw in the last video that instead of finding the area of this circle like we would with volumes and finding the disk and using the disk method, rather we're going to find its circumference. So this is going to be 2 pi r. And then we're going to take this circumference and multiply it by a little piece of arc length. By a little piece of arc length. And that's going to look like this. So something like that. And then multiplying those things together, we have this little piece of surface area. And that is what we saw in the last video. And now that we have this, again, all we need to do is apply this to our specific situation and then throw it into an integral and compute it. So let's see what we get. First, we need to find what r is. What are we going to say that r is? R under our graph here and how we represented it is going to be y. And we defined y as the square root of b squared minus x squared. So we are going to be integrating this guy with respect to x. We want to do that. And you can certainly integrate and set this up and integrate it with respect to y, but we're just going to integrate it with respect to x. It's just a decision that we're making here. So we have 2 pi, and we said that r is going to be the square root of b squared minus x squared. And then lastly, all we need to do is get this little piece of arc length. Get that little piece of arc length. So we saw a few videos ago, again, we can write this out, that ds is equal to the square root of dx squared plus dy squared. And we said we want to integrate with respect to x. So what we're going to do is factor out this dx squared and take it out of this radical. So we're going to be left with the square root of 1 plus dy over dx squared. And then we're going to have this dx outside the radical. And this is our little piece of arc length. And lastly, all we need to do is find what dy dx is. And we saw that y we defined as the square root of b squared minus x squared. So we said that y is equal to the square root of b squared minus x squared. And again, we could rewrite this. Could rewrite this as b squared minus x squared and all of that to the 1/2 power. And now we're just going to take the derivative with respect to x. So dy dx is going to be equal to, using some power rule and some chain rule, what do we got going on here? We have 1/2 times b squared minus x squared. Okay. And then we decrement that exponent. And then we have the derivative of the inside, which we're going to be multiplying by negative 2x. Minus 2x. There we go. Negative 2x. And that's what we have for our derivative. And now all we need to do is kind of simplify this guy a little bit. So we'll see that this 2 and this 2 will cancel. So we'll be left with negative x in this numerator. And then denominator-wise, we have the square root of b squared minus x squared. This right here is our derivative. And maybe to save us some time and some writing, we could just square this right off the bat, because that's what we need to do. That's what we're going to do when we throw this into our little piece of arc length. So let's see here. Let's square this guy. Just save us some time. We'll square this derivative value that we got. So we'll square this derivative. We're going to have x squared in this numerator, and then we'll have b squared minus x squared in the denominator. That's what we have when we square our derivative. Now, let's throw this into what we had for this little piece of arc length. So this is now going to be equal to the square root of 1 plus, and what do we find for our derivative squared? That is going to be x squared over b squared minus x squared. So that is x squared over b squared minus x squared. And then we still cannot forget dx. And this right here is our little piece of arc length. And now let me copy paste this guy. Right there. Okay. This guy comes right up here. And we just found what these little pieces of surface area are now. We just found that. And now we said all we need to do is throw this into an integral and get some limits of integration on that guy and solve it. And then we'll be done. Let's see here. Let's get a definite integral going. Definite integral. We'll throw limits of integration on last, and I'm just going to leave everything in purple now. So this is going to be 2 pi. I'm just writing out what we have down here. So 2 pi times the square root of b squared minus x squared. And then we have times the square root of 1 plus, and then we have x squared over b squared minus x squared, b squared minus x squared, and then we have dx. And then what are our limits of integration? If we're integrating with respect to x here, we can go from negative b to b, or we could recognize that, hey, we could use some symmetry. That might save us some calculation time. And that's what we're going to do. So rather than going negative b to b, I'm going to go 0 to b and then multiply by 2. So just using some symmetry. And now what we want to do is just simplify this guy. Simplify and solve. So we can throw this 2 pi out of our integral. We're going to have 4 pi outside of our integral times the definite integral from 0 to b. And then let's simplify this. We're going to have a square root of b squared minus x squared. And now on this radical here, I want to get a common denominator of b squared minus x squared. So that's going to be multiplying that by, if we get a common denominator of b squared minus x squared, we're going to be left with b squared in this numerator. And then we'll have b squared minus x squared in this denominator, and then we can't forget dx. Now, what I want to do is simplify this a little bit more, and this is starting to look pretty good. So we have 4 pi outside this definite integral, and we still have b squared minus x squared, taking the square root of that, and then numerator on this radical here, we're just going to have b. We're just going to have b, and then we'll be left with the square root of b squared minus x squared in this denominator, and then we have dx, and look at that, we get a nice cancellation. We get a nice cancellation right there. And remember, b, we're integrating with respect to x. B is just a constant, so this all comes outside of our integral. So we have 4 pi b times the definite integral from 0 to b of just dx, of 1 dx. And now, solving this, we're just going to do this. We're just going to write down the answer. This is 4 pi b squared, right here. This right here is our surface area. And maybe you knew the formula for surface area of a sphere. It's 4 pi r squared. And you can see we just confirmed that here. So hopefully what we saw in the last video, now you can start to get more of a trust behind what we were talking about in the last video. We have something more concrete that we're used to, that we talked about here, and hopefully you got some more practice with surface area, and we'll continue to get some more in the upcoming videos.